Hai guys, Assalamualaikum. So, hari ni kita akan discuss chapter 6.1 which is dynamic equilibrium. So, for this chapter, I'm going to explain what is reversible dynamic equilibrium and also law of mass action. Second one, we are going to look at the characteristic of a system in equilibrium. Okay, last one, we are going to interpret the curve of concentration, reactants and products against time for a reversible reaction. Di mana kita akan sketch graph lah. Okay, so let's get started. So, we have two types of chemical reaction. Okay, the first one is non-reversible. So, what is meant by non-reversible? Maksudnya reaction tu tak boleh patah balik. Okay, the arrow is one-way arrow. For example, okay, sodium hydroxide react with hydrochloric acid and form salt and water. Okay, maksudnya kat sini, once salt and water form, it cannot go back to the original form. So that is meant by non-reversible reaction. Okay, so for non-reversible reaction, when reactants are used up, the reaction will stop. Okay, reaction will stop. Contoh, kita goreng telur. Okay, kita goreng telur daripada telur mentah, raw eggs. So, telur masak. So, once telur dah masak, boleh tak you tukar jadi telur mentah semula? You cannot do that, right? Okay, so that is one of the example of non-reversible reaction. Okay, so the second one is reversible reaction. Okay, maksudnya reaction tu boleh patah balik. So for example, on our left hand side here is our reactant, here is our product. So maksud reversible kat sini adalah both reaction can proceed in both forward and reverse direction. So, maksudnya kat sini, hydrogen and iodine gas react together and form hydrogen iodide. So, once hydrogen iodide is formed, it can broken down into these two again. So, reaction boleh patah balik. So, the symbol we are going to use is reversible arrow. Okay. So, this is what I explained just now. Okay, so forward at equilibrium, okay, forward and reverse reaction proceed at equilibrium. And concentration, okay, at equilibrium, concentration of reactant or product remains constant. Maksudnya, once you achieve equilibrium, concentration of reactant and products constant, sama saja. Tapi ini bukan bermaksud concentration tu sama dengan kosong. Bukan ya. So, constant tidak bermaksud kosong. Constant maksud dia malak. Maksudnya static, tidak berubah. Okay, so that's the introduction for this subtopic lah. Okay, now let's have a look at the characteristic of a system in equilibrium dengan syarat, okay, in a closed system. Kenapa in a closed system? Kalau sistem terbuka, kita tak boleh nak tengok dia punya equilibrium lah. Okay, so if the question asks you, what are the characteristics of a system in equilibrium? So, the answer is these two. The first one, the rate of forward equals to rate of reverse reaction. Okay, maksudnya at equilibrium, kadar dia tu sama. Okay, kadar untuk forward reaction sama, kadar untuk reverse reaction also sama. Okay, so at equilibrium, all concentration of reactants and products, pressure, color are constant. Okay, maksudnya dia tidak akan berubah. Okay, so please add on in your notes what is meant by rate sebenarnya. Kalau ikutkan formula, rate is change of concentration over time. Okay, change of concentration over time. So this is the formula. So apa beza negative and positive? Negative is for reactant. Positive is for products. So why this happen? I'm going to explain this later. Cuma nak cakapnya, rate tu apa? Okay, rate adalah change in concentration over time. Berapa banyak perubahan concentration dalam tempoh masa yang diberikan. Okay, so next, let's have a look at concentration time graph of reversible reaction. Okay, so for the graph, first, of course, we need the axis. So axis for y is concentration, your x is time. Okay, so for example, let's consider this equation. A reversible with B. Maksudnya A boleh jadi B, at the same time B boleh jadi A balik. So at equilibrium, A jadi B, B jadi A at constant rate. Okay, now, so dia punya graf adalah bentuk gunting. Ni madam panggil bentuk gunting lah. Okay, gunting. Kenapa? Macam rupa gunting lah kan? Okay, so the first curve, okay, is when you start from the origin. Okay, kita tengok betul-betul lah. Start from the origin, the concentration is increasing. Put up until some point, dia jadi constant. Okay, so means that the first curve corresponds to our product. Ada ayam. Okay, that is for product. Kenapa product? Sebab at initially, bila time kosong, maksudnya reaction tak bermula lagi. But as time proceed, the concentration of product will increase. Okay, now, the second curve, dia start daripada atas. Kenapa atas? Initially, at the beginning of the reaction, the concentration of reactant is at maximum. Tapi, over the time, you guna A tu untuk hasilkan B. So, maksudnya A ni dia akan berkurang sampai satu tahap dia jadi constant. So our second curve is for reactant. Okay, label lah. Reactant. This one is product. So titik di mana dia dah jadi constant, itu adalah equilibrium point. Maksudnya sistem sudah mencapai equilibrium. System achieve equilibrium point. Cuba awak tengok. Even though the concentration is constant, but concentration A is not the same as concentration of B. Tengok graf pun tahu, the concentration is different. Okay, so that is the graph of concentration versus time. So if you asked to draw ataupun to sketch the graph, so the graph should be the scissor graph. Okay, so how to explain this situation? So as reaction proceed maksudnya semakin masa tu bertambah, concentration of reactant akan berkurang. Okay, this is the reactant. So concentration dia akan berkurang. Kenapa berkurang? Sebab dia nak hasilkan B. So rate of forward reaction decrease. Okay, rate of forward, kadar dia tu berkurang lah sebab concentration makin berkurang. Okay, so when that's happen, concentration product pula at the same time dia bertambah. Bila concentration bertambah, rate of reverse dia bertambah sebab ada banyak produk untuk hasilkan reactant semula. Okay, so at equilibrium, rate of forward reaction sama dengan rate of reverse reaction. Okay, and at equilibrium, kat sini lah, concentration of reactant and product remain constant. Bukan remains the same, remains constant. But concentration of A is not equals to B. So these all are the explanation to the graph. So you can revise on your own later lah. Okay, so that's the first graph. Our second graph is rate of reaction versus time graph. Okay, so again, we only consider reversible reaction. Okay, so first you have to have the axis lah, axis of rate versus time. Okey. Kalau tadi bentuk dia gunting, sekarang bentuk dia apa ni? Zip. Zip. Okay, so forward reaction, kalau forward maksudnya A plus B to form C plus D. So this is forward. Kalau reverse, C plus D form A plus B. Itu adalah reverse. Okay, now, so for forward rate, kita tahu tadi as time proceed, okay, as time proceed here, reaction akan slow lah. Okay, kadar. So the reaction becomes slow. Why? Because concentration of reactant decreasing. Okay, tapi at some point dia akan berkurang sampai satu tahap dia akan jadi constant. At the same time, pada masa yang sama, produk pula daripada tak ada, the rate is increasing. Okay, at some point dia berjumpa pula. The rate become equal with forward reaction just now. Okay, so when that's happened here, equilibrium is achieved. Okay, so maksudnya kat sini rate of forward equals to rate of reverse reaction. Okay, so that's the graph lah. Okay, so actually you only has 2 graph. Okay, so please understand this graph. Okay, understand the situation. It should be okay lah. Okay, let's try sketch the graph together. So you are given the reaction nitrogen dioxide dimerized as follow. Dimerized tu maksudnya change. Okay, sketch a graph of showing how the concentration of reactant and product vary during the course of reaction. Maksudnya dia suruh awak tunjuk graf macam mana concentration boleh berubah bersama dengan masa lah. Okay, so you have to know at this stage you need concentration and time graph. Okay, so first, kalau concentration versus time, so grafnya mestilah bentuk gunting. So first, draw the gunting first. Okay. Sepatutnya dia bersambung. Okay. Okay, bentuk gunting. Jangan lupa label. Okay, this is the initial concentration. Okay, so this is for kita punya reactant lah. Reactant kita NO2. Label NO2. So product is N2O4. Okay, so label reactant and product. Okay, make sure the curve is correct. Don't forget to tak kena. Sorry, I need to modify my graph. Yes, okay. So you can label at equilibrium. What else? So that's it. Okay. So first, concentration versus time exists. You akan dapat satu graph. You label yang betul, reactant and product dapat satu. Curve yang betul dapat satu. And don't forget to label equilibrium point. So you akan dapat satu. So total kalau sketch the graph, you will get 4 marks already. Okay, so that's how we sketch the graph. You don't have to worry at this stage. You don't have to use kertas graph yet. Okay, tak perlu guna. Just sketch. Okay, now let's go to the law of mass action. Okay, what is law of mass action? Okay, first kita kena tahu equilibrium law. For reversible reaction, at equilibrium and constant temperature, ratio of concentration of reactant and products has a constant value of K. Okay, dia nak cakap ratio concentration of reactant dan product ni dia ada value constant. Okay, so how do we determine the constant? First, let's consider this reversible reaction. Okay, so ratio of concentration of product to its power over concentration of A, concentration of B. So, according to the definition just now, dia cakap ratio of concentration of product and reactant has a constant value. So, constant dia adalah Kc. So, what is Kc? Kc is the equilibrium constant in terms of concentration. Okay, dia punya formula, jangan confuse. Kc ni adalah concentration of product over reactant. Bukan reactant over product, product over reactant to the power of its stoichiometry. Okay, so bergantung pada situasi dia lah. Okay, so macam mana nak tulis? So let's consider this following reversible equation. Kita ada methanoic acid form H plus and HCOO minus. Okay, now to write down Kc, tengok produk dulu. So our product is H plus. Okay, draw the square bracket. Square bracket corresponds to the concentration lah. Okay, cuba tengok stoichiometry kat depan 1. So maksudnya dia to the power of 1. Tapi kalau to the power of 1, kita tak tulis lah. Okay, so we have HCOO minus. Okay, dekat sini pun stoichiometry dia 1. So don't need to do the power lah, tak perlulah buat to the power of 1 over concentration of product HCOOH. So dapatlah Kc for this equation. Okay, so let's proceed lagi. If the reaction involve only gas species, the equilibrium constant ataupun equilibrium expression can be written in terms of partial pressure. Okay, let's say all these species here adalah gaseous species. Okay, gas. So, kita boleh tulis in terms of Kp. So, cara dia sama je, partial pressure of gas C to the power of C times partial pressure of gas D to the power of D over partial pressure of A to the power of A times partial pressure of B to the power of B. Okay, so Kp adalah equilibrium constant in terms of pressure. Okay, so maksudnya kita boleh tulis in terms of Kc ataupun in terms of Kp. So bergantung pada situation lah. So kalau dia ada phase gas, so you boleh tulis in terms of Kp. Okay, now let's proceed. Okay, example, write equilibrium constant expression in the following reaction. Okay, Kp. So check dulu semua phase gas. Okay, so partial pressure of carbon monoxide gas to the power of 2 times partial pressure of oxygen gas to the power of 1 divided by partial pressure of CO2 to the power of 2. Sebab dia ada stoichiometry kat depan tu. So itulah power dia nanti. Okay, so that's how we draw the write down Kc or Kp. Okay, let's proceed. Kita akan gunakan lagi Kc and Kp untuk 6.2. Okay, so next kita tengok types of equilibrium. So kita ada 2 jenis equilibrium. The first one is homogeneous equilibrium. Okay, di mana untuk homogeneous, reactant and product are in the same phase. Okay, so cuba tengok kat sini. Gas, gas, gas. So kalau phase semua species tu sama, so itu adalah homogeneous species ataupun homogeneous equilibrium. Kalau heterogeneous, okay, all reactant and product are in different phase. For example, this one, we have gas, solid. Ada je satu phase yang berbeza, kita akan panggil dia heterogeneous equilibrium. Okay, so for heterogeneous mixture, concentration of pure solid, pure liquid do not appear in the equilibrium constant. Kenapa dia tak muncul dalam KC or KP? Sebab dia punya concentration of pure solid and liquid do not change much with temperature. Okay, so itu reason dia lah. Okay, for example, let's have a look at this equation. Kita ada solid, liquid and gas. So basically this is heterogeneous equation. Tapi untuk heterogeneous, kat sini dia dah cakap, kalau dia ada pure solid, pure liquid, kita tidak akan tulis dia di dalam expression KCO, KP. So for this case, kita boleh cancel out solid dengan liquid phase. We only consider gas or aqueous phase. So cara tulis dia KP sama dengan P of oxygen gas. That's it. Okay. Tak perlu buat tak perlu masukkan HGO dengan mercury liquid. Okay. Next, we have solid, gas. Yang solid tu kita boleh cancel. Sebab kita tak akan tulis dalam KC or KP. So, in terms of pressure, KP equals to partial pressure of CO2. Kalau KC, in terms of concentration of CO2. Okay. Next. Okay, next, number 2. Number 2, kita ada solid, liquid, solid. Again, partial pressure of, kalau soalan nak KC, so you akan jawab KC sama dengan concentration of C2H2. Kalau soalan nak KP, partial pressure of C2H2. Bergantung pada soalan lah. Okay. So next, kita ada the third equation. Kita ada gas, solid. Okay. So for this case, kalau dia nak KC, for example, tapi kita kan tahu the formula is concentration of product over reactant. So kalau produk kita dah cancel, macam mana kita nak buat? So for this case, we are going to write down 1 over. Okay, 1 over concentration of ammonia times concentration of HCl. So kalau KP pun sama lah. KP sama dengan 1 over partial pressure of ammonia times partial pressure of HCl. Okay, last one, number 4. Okay, solid, kita cancel. Okay guys, kalau aqueous, kita tidak akan, kita tak boleh tulis in terms of KP. Sebab KP only for pressure. So, kita boleh buat dia dalam, in terms of KC lah. So, H2S2O3 divide by H2SO3. So that's it. Senang je kan? So that's how we write down KC or KP. Cuma ingat kalau kena tengok phase of the reactant and product betul-betul. So kalau solid and liquid, we can cancel it out. Okay, one more thing. You don't have to worry about the balancing, about the equation. You don't have to worry because the question will, there will be in the question for you. So tak perlu nak fikir nak balance ke apalah. Okay. So that's it for 6.1. So I will see you for 6.2. Okay. Thank you. Assalamualaikum.